In this lesson, we will look at the phenomenon of turbulence and wind shear, how they are created, and their impact on aviation. Turbulence means disturbed or rough air which disturbs the aircraft's attitude but allows the aircraft still to maintain its flight path. Wind shear is a similar phenomenon but far more severe. It is not rough air as such, but airflow that has marked variations in speed and/or direction. Wind shear differs from turbulence in that it will displace the aircraft abruptly from its intended path, such that substantial control action is required to maintain heading and speed. One of the most common causes of turbulence is the surface over which the airflow is moving. The layer of air that is disturbed is known as the friction layer. Above this friction layer, the airflow is unaffected by the surface. The boundary of the disturbed upper flow is called the friction level. Turbulent air near the surface is created in two principal ways. Mechanically, by objects like trees, hills, and buildings, and thermally, through the effect of warm air rising. We call these effects mechanical or thermal turbulence, respectively. It is not just near the surface that we find disturbed air. It is also found around significant cloud developments. Looking at the diagram, we see cumuliform cloud created by rising air. This vertical flow of air will disturb the free air, creating turbulence within the cloud. The vertical extent of the cloud is therefore a very good indication of the intensity of the vertical airflow and therefore the intensity of the turbulence. For this reason, cumuliform clouds are treated with caution in aviation. Cumulonimbus clouds are the most visually obvious in terms of their capability of generating turbulence. However, we don't just find turbulence within the cloud itself. If we now consider the bigger picture, we can identify downdrafts at quite some distance from the cloud. These currents can also disturb the free air, likewise causing turbulence. Very large cloud developments like cumulonimbus will have very active downdrafts and must be treated with extra caution. There is one added concern with large cloud developments, particularly of the cumuliform type. When precipitation falls from clouds, it tends to drag air down with it, creating downdrafts within and underneath the cloud. If the amount of air descending from the cloud is significant enough, then a phenomenon known as a microburst or macroburst is experienced. When the air descends beneath the cloud, it may come into contact with the ground and then spread out. Because of the very large changes in the direction and speed of the wind, both vertically and horizontally, this gives rise to very dangerous low-level wind shear. There is another area where the airflow can be significantly disturbed to generate significant turbulence and potentially very hazardous conditions. Looking at the diagram, we can see a mountain with horizontal airflow from the left. As the air flows over the mountain, it starts to oscillate in a wave-like pattern. These oscillations are known as mountain waves, lee waves, or standing waves. To create the oscillations, certain conditions must prevail in the atmosphere. Firstly, the air must be very stable, otherwise the airflow when reaching the mountain would rise vertically and destroy the oscillation pattern. Another condition which must be met is that the wind speed at the level of the ridge must be greater than 15 knots and increase with altitude. The direction of the wind in relation to the mountain's orientation is another crucial factor. There must be a significant proportion of the wind close to the perpendicular of the mountain axis. The diagram shows an example of a mountain range aligned north-south. The direction of airflow that is needed to help create the mountain wave must either be from the left or the right. If all these conditions are met, the mountain wave will be created. Often these oscillations may become visual. When the air is forced to rise at this point, it will cool adiabatically, condensation may take place and cloud may form. However, when the air is forced to descend at this point, it warms adiabatically and any cloud dissipates. Notice the shape of these clouds. Particular features of this cloud are that they have a lens-like shape and that they are often stationary, the cloud continuously forming at the leading edge and dissolving on the trailing edge. These clouds are called lenticular clouds. There are other visual clues of the mountain wave for the pilot. One of these is the cloud that shrouds mountains, making it difficult for the mountain to be seen from the air. These clouds are called cap clouds. There is one other cloud that is probably the most significant, since it implies the location of the most severe turbulence. If we look at the flow of air underneath the first wave crest, we can observe a rotation of air. This zone is the most dangerous, since the wind direction is changing constantly within a very confined area. The clouds that develop here are called rotor cloud or roll clouds. There is another situation in the atmosphere that can give rise to turbulence and wind shear. In the lesson on temperature and pressure systems, we said that there may be times when we can experience temperature inversions. You may recall that inversions are where temperature increases with altitude. These tend to be confined to the very lowest layers of the atmosphere close to the surface. If the temperature inversions are strong enough, then as a result of the changing density, we can get significant changes in wind direction and speed through the inversion. This leads to wind shear, and as pilots we need to be made aware of them. Be extra cautious if your destination airfield issues an MTI. This stands for a marked temperature inversion. Receiving an MTI should prompt you to be extra cautious of wind shear around the airfield and on the approach. Though beyond the scope of this course, we will make brief mention of mixing in the lower layers of the atmosphere, creating inversions. Where mixing occurs, temperature falls more rapidly with height. But at the altitude where there is no mixing, the temperature is a little higher than within the mixing layer. These inversions, like any other type, need careful consideration because of the wind shear they can create. Turbulence of any kind is something we wish to avoid. It is especially dangerous to aircraft on the approach or during the landing phase of flight, since the aircraft has low forward speed, low altitude, and high amounts of drag. Fly with great caution, respond promptly to turbulence, and monitor your airspeed closely. Use a slightly higher takeoff or landing speed to ensure a greater safety margin from your stalling speed. But be wary, this will increase the landing and takeoff distance. From this lesson, you will hopefully be more informed about turbulence and wind shear. This will help you to be prepared and more able to make correct decisions about avoidance.